Hey everyone, Geophysicist Stefan Burns here. The enigmatic interstellar object 3I Atlas is continuing to morph in front of us as it travels into the inner solar system, soon to perform its perihelion, its closest approach to the sun, around October 29th of this year. Now, most people are saying that 3I Atlas is a comet. I'm calling it an interstellar object because we still don't know exactly what it is. And well, new data is coming out that supports that unclassified designation because it continues to defy our typical understanding of comets and also of asteroids and dwarf planets and many of these other minor objects that exist within our solar system. 3I Atlas is from interstellar space, and so it's from a completely different celestial neighborhood. We don't know really under what conditions it formed, and therefore we should in general expect that it's going to be quite a bit different than it is. And while we have these polarization measurements now of 3I Atlas going from July to August, and it's quite striking because it shows the growth of 3I Atlas as it gets closer to the sun during that time frame. It's going to continue to grow with its coma, this combination of gas, dust, and plasma. It's already half the size of the sun, getting bigger each day, and also showing unique structures within this coma. At least that is what the polarization data is suggesting. And we also just got some new imagery of 3I Atlas from Nambia taken during the lunar eclipse, and well, it's now glowing green. Though bizarrely, it's depleted in the elements needed for a comet typically to glow green. So if it is glowing green, how is it doing so? And we also already know, based off of a bunch of observational evidence, that it has a dark reddish color to it, and that's very common for trans-Newtonian objects like Sedna and some of the others that go outside the heliosphere. It seems that being exposed to the interstellar environment turns these objects red. And so it has a dark red color, but now it's glowing green. It's getting bigger day by day, and it has this unique plasma structure surrounding it. That's at least what the polarization data suggests. Let's get right into it. A new research paper just dropped on 3I Atlas, and it's titled Extreme Negative Polarization of New Interstellar Comet 3I Atlas. I'll link this in the video description, as well as a bunch of other research papers on this interesting interstellar object and some related research that you should read as well to come to a more comprehensive understanding of this topic in general. So check that out. In the abstract, they say 3I Atlas represents a distinct type of comet. But if you go further down, we get a bit more detail. It's a little bit more nuanced than that. What they say here is that 3I Atlas possibly represents a previously unobserved class of small planetary bodies. That's quite a bit different than just a comet, because comets are these low density little objects that fly in, and they have these gas and plasma and dust trails behind them, even elemental tails, and they do a lot of very interesting things. And they typically have this high eccentricity orbit that takes them out way beyond the solar system, and then they zoom back in because the pull of the sun brings them in. There are a lot of other objects in the solar system. We also have trans-Newtonian objects which exist beyond the orbit of Neptune. A lot of them are dwarf planets that are gravitationally around it. Not all of them are. Haumea, for example, is oblong, though it is huge in size. And so we have a whole bunch of very weird things that exist outside the orbit of Neptune. There's also a whole bunch of objects that exist within the orbit of Neptune going to the sun. Things like centaurs, which are basically very large asteroids, but sometimes they exhibit cometary behavior. So they do this off-gassing occasionally. We saw that with the asteroid Chiron. We've seen that with other asteroids as well. And sometimes they do it at distances from the sun where we typically would not expect cometary behavior, because that's driven by solar radiative influences in general. So 3I Atlas possibly represents a previously unobserved class of small planetary bodies coming in from interstellar space, and basically we don't have a definition for it, but there's some interesting data presented in this research paper that really tells a story about the growth of 3I Atlas as it's been zooming through the solar system, and also its unique plasma structure. Let's check it out. Now, before we spend some time on this graphic, which is very illustrative, but it takes a little bit of time to understand, we are going to focus on this one here. And this one tells a story. So first and foremost, what are we looking at? Well, we have 3i Atlas right here. This is July 19th. We see different images of 3i Atlas across time. Okay, so here we see July 22nd, the 24th, the 30th, 12th of August, 21st of August, and you'll notice that this scaling there is the same for all of these. So we clearly see how this dusty, gassy, plasma-rich coma surrounding 3i Atlas has been getting bigger during this time frame. That is very, very clear. We also see that down below. Here we see the polarization values for these light photons that were collected effectively. So we are just observing the sunlight reflected off of 3i Atlas. There also could be a bit of internal light generation. This is possible with plasma. Plasma can generate its own light. So that's an easy way to explain that. But here we see this polarization of the coma, and we see that across time. And well, it's not just kind of like a homogeneous polarization. It has clear structure to it. And here we see the degree of polarization. So this is -6 degrees and then going all the way up to +5 degrees or so based off of this heat map. And then right in the center there is green, that's 0. One thing you'll notice is that the center of all of these effectively is right near 0, especially these last two. You'll notice that it is fairly homogeneous with its polarization here and here, but it's on the outside that you get these swings in polarization. And so here you have really low polarization, or at least it's -6% there, deviated away from just normal scattering of light. But then you also see this ring there of positive polarization, basically equivalent on the other side. Almost looks like a double layer, which we know that plasma forms. We see the same thing right here, though it's more skewed to the positive. And we also see here, back on July 24th, a very weird structure there, dominated mostly by positive polarity light reflectance. So whatever this is, it's primarily reflecting light with a positive degree of linear polarization. We'll talk about what polarization is. But just showing that there is clearly a structure that has evolved on 3i Atlas. So not only has it grown across time, but it's also become more complex. This is what our light polarization data tells us. So what is polarization? Polarimetry uniquely probes physical properties of an object, such as optical constants, grain size distributions, and dust shape and structure in the case of a cometary coma or surface regolith. That's the surface of an object like an asteroid or a comet, whatever. And this is not easily inferred from other techniques, making polarimetry really useful. The degree of linear polarization of sunlight scattered by cometary dust particles is measured as the difference between the fluxes perpendicular and parallel to the scattering plane, Sun-Comet observer plane, normalized by their sum, and is highly sensitive to the solar phase angle, alpha, Sun-Comet observer angle. By this definition, polarization is positive when the polarization direction is oriented perpendicular to the scattering plane and negative when parallel. Overall, solar system objects show similar phase angles, negative polarization at small phase angles, and positive polarization at larger phase angles, increasing nearly linearly until reaching a maximum at around 90 to 100 degrees. So that was quite a lot, but let me now break it down. Let's learn what polarization is. We are going to go back to that data slide, but first we have to see what polarized light is in the first place. And so we have light. This is basically what the sun is emitting. We also emit it through our bodies. There's a whole bunch of things that emit light, your light bulbs, so on and so forth. We all, in general, know what light is. Well, light can be thought of as not only as a particle, but also as a wave. It's one of the kind of the conundrums of physics. And as a wave, it has its propagation direction, right? So it's a vector of motion. And then we observe that the electric field that is inherent with this light wave also has a magnetic field. They're orthogonal to each other, and together they move forward through space like this. Polarized light is light that has been confined to a very specific angle, whereas unpolarized light, like what the sun emits or a light bulb in general, is occupying all those different angles. So you see this right there. Imagine that completely filled in 360 degrees. You have some light at this angle, some light at that angle, so on and so forth, and it forms a full 360. If you can polarize light, then you can control which plane, right, that 2D plane the electric field is propagating on, and also that 2D plane that the magnetic field is propagating on, orthogonal, or rather 90 degrees to that electric field. So here we see the unpolarized light. Let's say this is sunlight, and we have this filter there, very similar, you could say, to the sunglasses you put on that are polarized. They cut some of that errant light that's being scattered from weird angles, right? Like the bottom, like the asphalt of the road in front of you, so you can see without glare. It cuts those angles out, only allowing in certain angles. And well, now we have light that is still propagating the same vector direction, but only the electric field is propagating, let's say, in the vertical plane, and then the magnetic field in the horizontal plane. So that is linear polarization of light. You also have circular polarization, where it's continuously being rotated, but for the purposes of this video, we only really need to understand linearly polarized light. So basically, we observe these comets or objects or whatever in space, and there is sunlight that's hitting them, and that sunlight is unpolarized, and we get some of the reflected sunlight back. And what we observe is that things like ice crystals and other little microstructures or dust grains can slightly polarize light. So it's not that we're just getting purely unpolarized light back to us. We get some degree of linear polarization as deviated away from normal unpolarized sunlight. So that is what they're looking at with 3I Atlas and with all these other comets. They are determining the degree of linear polarization, and then that also changes depending on the angle that we are viewing it at. And so if you have, for example, an object really far away from the sun, the Earth is close to the sun. And so our angle difference between the sunlight vector and our observational vector is quite minor. So trans-Newtonian objects, for example, we only have phase angle linear polarization measurements in like that 0 to 3 degree range, because all of them are beyond Neptune, and well, we haven't really viewed them from the side yet, which would be useful in diagnostic, but we simply haven't done it yet. But comets, they fly into the solar system and they swing through pretty close typically. That allows us to then also observe them from these other phase angles. And that allows us to create a plot of the phase angle versus the polarization. And that is a diagnostic on just some of their overall features and characteristics, and can help us understand their coma better, and the ice grains and crystals and dust grains and more, the surface regolith. So the degree of light polarization coming off of an object is quite descriptive, though it is a little complex to understand at first, but it is very useful, and we have those measurements for 3I Atlas. Now we can better understand what we're looking at here with that information in mind. So you have the sun observer object plane. That's what we're viewing this light across, the scattered light. And then we also have the angle between the sun, the observer, and the object. And that changes how we view the light being reflected from that object, because polarization is directionally based, okay? So we have these here. Again, I pointed out how they are not homogeneous. There's quite a bit of differentiation within these data graphics, at least showing the differentiation of the light polarization being scattered off of these objects. So sunlight and maybe a little bit of internal light generation that we're receiving. And it shows clear, distinct structure. That's very common with plasma. Plasma will form very clear, distinct structures within it, and it can maintain that structure across time, especially in conditions out in space. And as a result, it can also form these locked magnetic field configurations, and powerful electric circuits will propagate within the plasma. It gets really interesting. One of the key structures of plasma are what are known as double layers. And so you have a very high electric potential paired really close to a very low electric potential. So big positive charge, really low negative charge, the two create a gradient. So this is that double layer. You get this acceleration of particles when they travel through that electric field gradient. Well, electric field, light polarization is telling you the direction of the electric field. And so here we clearly see that. And we see this double layer structure on a very large scale. At least that's what this is indicating to me. This border there on the inside of positive polarization, and on the outside there of negative polarization, that degree of polarization, that's very interesting. And this negative polarization is the light wave, the electric field of it turning more parallel to the sun, observer, and comet or 3i Atlas plane. Whereas if it's positive, it's more perpendicular to it. So it's showing that there are clear, distinct differences in the electric fields around and near 3i Atlas within its coma, which, well, if it's composed of gas and dust, and we know that gas gets ionized in space, that immediately makes it a complex, dusty plasma with some percentage of neutral gas. And it's dominated primarily by carbon dioxide, but it also contains water. There's also water ice, which we know can form very unique, highly ordered, and information-rich crystal structures. It seems to imprint upon whatever information is in the area around it. You can check out the work of Veda Austin for that, where you'll get these flash frozen ice crystals to actually preserve the image of a photograph placed directly underneath them, or a thought form put into them. It's incredible, fascinating research. So we have all these dynamics in place. You have plasma, you have the intelligent ice crystallography that can exist out in space because it exists here on Earth, and we see it's getting bigger as it's getting closer to the sun. It's forming a more complex and differentiated structure. 3i Atlas is unlike anything we have ever seen. And that's backed up by this data here, also from this research paper. So here we see the polarization versus the phase angle of 3i Atlas against other celestial objects. And so this allows us to kind of just form a default characterization. Right off the bat, this gray line there is an average line for most comets. Most comets have a polarization versus phase angle distribution like that. And so it'll reach a negative polarization about negative 1.5 at a phase angle just a little bit less than 10, so about 8 or so. That's kind of that bottom dip right there. And then that inflection point, which is very important, a diagnostic for this, for most comets is about 20. That phase angle of 20 means it shifts from negative polarization to positive polarization, and then it continues on upwards with positive polarization all the way up to that 90 to 100 degree phase angle. Again, that observer angle is now more square. We see a very unusual comet, which is a C. Halley-Bopp comet there, and that has just very few comets in that category because it had this very extreme negative polarization there, and then it had a steeper slope on the positive polarization. Well, 3i Atlas is one of the most bizarre, if not the most bizarre objects that we have ever observed, at least as it relates to polarization. So 3i Atlas is this black curve here. We do not have data for this. This is an extrapolation of the curve based off of some known math because we have really good data for these others. We can kind of calculate the curve. So this is our first measurement there at the lowest phase angle degree. 7 degrees, negative 2.7% for that linear polarization, making it a little bit more aligned and parallel to that sun, observer, and object plane. And then it has this inversion there where it goes from negative to positive in the polarization at a very low phase degree, about 17 degrees, which you see is quite a bit lower than most comets, and also this very unusual category of comets defined by C. Hale-Bopp there. I hope I'm pronouncing that right. So 3i Atlas is very bizarre if we look at it from the perspective of other comets that we have observed. Also, as we view it from the perspective of Borisov, that other interstellar comet that flew in 2019, we see those measurements there. We see that its inversion was quite a bit further back, around 20, 21 degrees. in line with this unusual category that's shown in green. So that was already odd. Well, 3i Atlas is very bizarre. Now on this side, we have it compared to other objects in our solar system. We have F-type asteroids. Then we also have some specific objects that have really odd polarization curves. And we also have trans-Newtonian objects. Remember how I said we only have this polarization data for TNOs in that like 0 to 3 degree range just because they're so far out, right? It really helps illustrate that angle that we can cut and see them at. Well, here is the data for the TNOs. And again, this curve there is an extrapolation based off of what we have and also the mathematical formulas. It's probably pretty close to accurate, but we won't know until after it's perihelion and we can get some of those measurements when it's zooming out of the solar system. If it does that, we'll find out. But it is very similar to TNOs at least. This extrapolated data is very similar to these trans-Newtonian objects. And so it's really looking like it's quite a bit different than a comet, quite a bit different than an asteroid, quite a bit different than these centaurs or other objects that we know of, and more similar to trans-Newtonian objects, which we know exist in our solar system, but way, way, way out there, and they have these incredibly elliptical orbits. And so maybe interstellar object 3i Atlas was some sort of distant object in its own system that just got booted out, but somehow at super high velocity. Again, it's traveling about 60 kilometers per second. At its perihelion, it'll be 68 kilometers per second. That is incredibly fast. That is super fast. We've never observed an object traveling through our solar system at that speed. It is setting an absolute speed record. So the list of unusual things keeps adding up as it relates to 3i Atlas. And the reason we spent so much time on this slide here is because we were looking at the differences in the polarization. This slide does not show you those differences in the polarization with the structure across time. It just gives you that average polarization at that phase angle, which is linked to a specific observation date. So you miss the bigger picture if you don't look at this data, which shows these very clear structures to 3i Atlas. So now we're seeing this clear structure form that's more than just a coma. It is starting to form a little bit of a tail, but nothing like most comets. It did have this unusual sunward facing tail, you could say, a little bit of a push of ice crystals and dust and gas sublimating out on the sunward side when it was further out. No other comet has ever been observed to do that. Now it has more of a normal tail. We can kind of see that in these images there. And well, the latest observation is that it's actually now glowing green. Here we have an article from spaceweather.com. I'll also link this in the video description if you'd like to check this out. And well, on September 7th, during that total lunar eclipse, some astronomers took the opportunity to photograph 3i Atlas from the Kalahari Desert in Namibia. And here is what they saw. They see 3i Atlas in pretty good detail, not the detail that we had with Hubble or some of these extremely powerful telescopes in space or on ground, but they did image it. This is a pretty good photo. It's the most recent one that we have of any quality, and it's glowing green. So it does have this reddish color to it. That's what we observe with a lot of these trans-Newtonian objects, and that's what we've been observing with 3i Atlas based off of the spectrum data. But now, as it relates to just optical visual light measurements, it's starting to glow green, which comets do. But this is very interesting because this is a familiar sight. This is what the article says, that comets will glow green, but typically the emerald hue comes from diatomic carbon, or C2, which fluoresces at 518 nanometers when energized by sunlight. 518 nanometers being within that range of optical visible light, which is about 350 to 750 nanometers. Well, the weird thing is that 3i Atlas doesn't have that much C2. At least that was what the data suggested back in July and August. Maybe now that's closer to the sun, somehow C2 production has turned on. But if that is not the case, then it is glowing green through some other complex mixture of gas and dust, and it's doing so via unfamiliar chemistry. That's at least what the article says. So Very, very bizarre. Now 3i Atlas is also glowing green in addition to these new revelations that we've had with 3i Atlas and the fact that it's growing bigger day by day as it gets closer to the sun, and it seems to be forming increasingly complex structures within that complex dusty plasma coma. And let's perform a status update as to where 3i Atlas is right now in the solar system and where it's going to go, at least based off of the current data of its trajectory. So here we have a web app, the Sky Live. I'll link this down in the video description. Super useful. We see 3i Atlas there. Its orbit there is highlighted in green. We also see the inner solar system, so Mars, Earth, Venus, Mercury, the Sun, and then I loaded in also the first 20 asteroids just to get a sense of the asteroid belt, because they have a variety of orbital locations and eccentricities and inclinations. And so we see that 3i Atlas right now is zooming through the asteroid belt, which does extend above the ecliptic plane up to about 30 degrees. And eventually 3i Atlas will swing right through the ecliptic plane, and then down, it'll be below the ecliptic plane. That'll be later in the year. But this is where it is right now today, September 11th. And we're seeing it's getting closer and closer to Mars. It has its closest approach to Mars on October the 3rd. So we see it get very close to Mars right here. This is its closest approach. Still not within its orbit yet, but just within like 0.2 or 0.3 astronomical units. And we have a reconnaissance probe that's orbiting around Mars that will be able to take a high-resolution photo of 3i Atlas. So we can finally understand how big its nucleus is. That's the big unknown right now. We don't know how big this object that is traveling through the solar system is. We have a lot of data on this coma that's surrounding it, but the actual object itself is basically an unknown. The size estimates are all based off of understandings of its albedo. And so if you don't get that albedo measurement right, you're not going to get the size estimate correct. So we really don't know the size. The upper estimate right now put out by one of the research groups is about 50 kilometers in diameter. Some of the lower bounds are like 0.2 kilometers in diameter. So it's all over the place. But we see this really close approach there on the 3rd. To Mars, and then if we go forward to the 21st of October, we will see our superior conjunction that we have with 3i Atlas. Earth there is being very cautious, basically, because 3i Atlas is getting very close to Mars, it's getting pretty close to Venus, and very close to Jupiter. And this is a very high-speed, large interstellar object. You wouldn't want that hitting the planet, right? That would be cataclysmic. Like, with that speed, which is much higher than most asteroids, and that size, which could be up to 50 kilometers, it would literally be cataclysmic, like we would all die. So Earth is being very smart and being on the opposite side of the sun during that nearly that perihelion closest approach. And so we get the superior conjunction there on the 21st, and then if we go forward to 29th, that is right around when we have the closest approach to 3i Atlas, as you can see there. That around that time period is when I expect there to be a lot of solar activity, because 3i Atlas is this very large object with a very complex coma surrounding it, full of dust and gas and plasma, and it's traveling along the ecliptic plane. So I think all of October and November is going to be characterized by heightened solar activity at times, and probably some big X flares. And then if you go forward all the way to March, that is when 3i Atlas gets very close to Jupiter. So I will keep you up to date on what is happening with 3i Atlas on the channel. So please subscribe to stay informed. I'm looking at all this data and research as it's coming out. Again, I've been your host, Stefan Burns. Thank you all so much for watching. Wishing each and every single one of you well. Please take care of yourselves. I'll see you all in the next video.